Sorry. Oh. That's the thing. What's what? Oh. Oh, good.
On this side of the using out obvious when the switch happened. There was broken. Yeah. All right. All right. Everything?
Yes.
All right. Hi everyone. Welcome to our ANC seminar. So today we are very happy to have Bardiya visiting us from ICT Austria, who works with Monica and Steiner on differential privacy and this dynamic algorithms, continual release. So we are going to hear about combination of both.
Yes. Thanks for the intro, and I'm very happy to be here today. This talk is going to be on our recent paper, Improved Lower Bounds for Privacy under Continual Release, which is going to appear in PODS this year. And it's a joint work with my advisor, Monika Hansinger, David Solpik from ERIF, France, and Zuri Sharon from University of Vienna. And feel free to interrupt me whenever. So first things first, the definition of privacy that we will use is epsilon delta differential privacy, also known as approximate DP. I won't spend too much time on this definition because I'll try my best to keep the differential privacy parts in a black box as much as I can. But intuitively, this definition is saying that we say that an algorithm A is differentially private if for any pair of neighboring inputs, x and x prime, the output of the algorithm A on these two has, let's say, closed distributions. More formally, we say that the algorithm is epsilon delta dp if for any two neighboring, which we will define based on the context, databases x and x prime and any possible output sets, the probability of the first one being in this, the output of the first one being in the set S is at most e2 epsilon times same probability for the second input plus some extra probability delta. So the setting that all of the results in this paper are on is differential privacy under continual observation, which is DP community way of saying dynamic algorithms. So we have T updates. After each one of these updates, we have to output based on whatever we've seen so far. And well, this part is not always true, but at least in the event level setting, we call two streams neighboring if they're only different at the event of one of the updates. But I'll get to that later. And we say that an algorithm is alpha accurate if with probability at least 2/3. Its additive error is at most alpha for all of the time steps simultaneously. So without further ado, let's get to the first set of results that I will talk about, which is on some graph problems. So when it comes to continual DP for graph problems, there are a lot of different ways, a lot of different settings that one can look into. Well, first of all, we have edge differential privacy versus node differential privacy, which in edge DP, At each one of the time steps, one edge is updated, either inserted or removed. Whereas in node DP, at each one of the updates, all of the edges incident to one node are subject to change. And then, as I mentioned earlier, we have event level setting, which in each one of the updates, well, in two neighboring streams, only one event of one update at one of the time steps can change. But in the item level, all of the updates corresponding to an item, whether an edge or a node, can change. And also, of course, we have insertions only versus fully dynamic, where in insertions only, we only have insertions. And in fully dynamic, we have both insertions and removes. So just as an example, for example, if you're looking at insertions only edge differential privacy, then events level and item level are the same because we can insert that one edge only one time. So in all of the results in this paper, we consider edge differential privacy. In the paper, we have results on both event level and item level. But on the results that I'm going to talk about today, we only consider event level. And I will talk about both insertions only and fully dynamic. But the fully dynamic part is more towards the prior work parts of the talk, and our work is on insertions only. So to wrap it up, we have T updates. At each one of them, we have one edge either inserted or removed. And two streams are called neighboring if only one of these updates is different between the two. So let's see what we already know in terms of lower bounds for graph problems in continual DP in this setting that I mentioned. Well, in the fully dynamic setting, there was these two papers last year that showed lower bounds on the additive error that are polynomial in n, the number of nodes, and t, the number of time steps, for a variety of problems like maximum matching, number of connected components, and triangle counting. But in the insertions only, there was only this paper in 2021 that showed some lower bounds that are polylogarithmic in n and t. And that was again for a variety of problems, like again, maximum matching and degree histogram.
Andrei, can you say these results explicitly? Like, what do they prove?
Yes. So, for example, for maximum matching, their results is minimum of t to 1/4 and square root n.
So your additive error from the size of maximum matching has to be that.
Additive error for the size of the maximum matching.
Regardless of
regardless, yes. These are information theoretic lower bounds.
Regardless of the time that it takes, you need to add, like your error has to be square root n.
Square root n, yes. Minimum of square root n at t to 1/4, yes.
Is there any upper bound?
The upper bounds are t to 1/3. So there's a polynomial gap there.
For the insertion of the model, so the neighboring definition is that we change the insertion of one.
Yes. Instead of inserting this edge, we insert that edge.
Yes,
Or we can just swap it with a no-op, which are just up to constants equivalents. Yeah. Yes. So as you can see, there is a gap here. By the way, just to give you an idea of how people think of these results in the field, we normally think of those problems with polynomial lower bounds under additive error as difficult problems, and these ones, well, not these ones, but the ones that have polylogarithmic upper bounds as easy problems. So as you can see, there's this gap here that for fully dynamic, we know that a bunch of problems are hard. But for insertions only, we don't know much. So this
One last question is, what's the dependence on epsilon and delta?
it's polylog 1 over delta and polynomial 1 over epsilon.
For both?
No, for the lower bounds that we have here, they're actually on constant epsilon, constant delta. There, if the lower bound holds for 1 epsilon and 1 delta, it holds for everything smaller than that because it's more private. But the upper bounds that I mentioned, they have inverse polynomial in epsilon. Yes. So this raises a natural question. Well, are these problems hard because of the problems themselves, or are they hard because we're looking at the fully dynamic setting? In other words, if we consider the insertions-only model, will we be able to get polylogarithmic upper bounds, or will we again have polynomial lower bounds? Well, as the title of the talk suggests, we found polynomial lower bounds for quite a few problems in the insertions-only setting. In the paper, we have a framework to formalize the mutual idea of the lower bounds. And then we show for each one of these problems that they fall into that framework. And we show that every problem that falls into that framework has the lower bound holding for it. But today I won't bother you with the formalisms of that framework, and I will only show you the gist of it through showing you how it will work for maximal match. So let's see how we show this lower bounds. In our paper, for all of the events level lower bounds that we show, the theme is that we use reductions from this problem called inner product queries. In this problem, we have a private vector x, which is a d-dimensional binary vector. And we have m queries, q1 to qm, which each one of them is also a d-dimensional binary vector. And we want to output the dot product of the private vector with each one of these query vectors after receiving the queries. Well, the lower ones that we use actually hold for receiving all of them in a batch as well, but it's not necessary for us.
Sorry, I have a question about, are you going to be looking at general bipartite matching or sorry, general matching or bipartite matching?
It works even for bipartite.
Okay, even bipartite.
Both the one in Raskhodikova and Steiner paper and ours. And two instances of this problem are called neighboring if they're different in only one of the bits of the private vector. So the query vector is not private at all. And yeah, two instances are different if one bit of the private vector is different. So the thing about this problem is that we know that it's hard. In the sense that we know that there is no differentially private algorithm with epsilon smaller than 1 and delta smaller than 1/3, which is too generous, by the way, that can answer omega of the number of queries with additive error O tilde of square root d. So is there any questions up to here? So let's see how we can use this problem. We can use reductions from this problem to show lower bounds for our problems. So we have an instance of this problem, and as I said, I'm gonna only talk about maximum matching. So we have a black box that solves maximum matching, and we want to use that to answer the instance for inner product queries. Yes. So the idea here is a very natural thing. We want to think as this dot products for each one of the bits as AND gates, and we want to simulate AND gates with instances of maximum matching. So let's first see how Raskhodikova and Steiner did it for the fully dynamic setting. Then I will tell you what will go wrong if we want to do the same for insertions only. And then I'll tell you how we fix it for the insertions only setting. So first assume that D is equal to 1. So we have only one private bit and one query bit for each one of the queries. Let's think about this graph over there. For vertices, we always add that vertical edge over there. And the edge E1, we only add it if the private bit is 1. And the edge E2, we only add it if the query bit is 1. So now this graph, if both of these edges are present in the graph, the size of maximum matching is 2. But in any other cases, the size of the maximum matching will be exactly 1. So for each one of the, if we just add that E1 in the beginning, and for each one of the queries, we put E2 if the query bit is 1, and we take the size of the maximum matching and subtract 1, we will have this AND gate simulated. So for the reduction overall, we can just have one of this gadget for each one of the D entries. In the beginning phase, we add this E1 edges for each one that we have to. And then for each one of the queries, we add the query edges E2s that we want. We take the size of the maximum matching, answer the query, and then undo whatever we did, which means we remove all of the edges E2 that we inserted. And also note that in this reduction here, neighboring instances of inner product queries map to neighboring instances of maximum matching. So if one private bit is changed, only one update in that initialization phase over there will change. And in this reduction, since they use order of the vertices and order of the squared updates for the queries, the lower bound that it will give us is t to 1/4 and square root n, minimum of the two. Let's.
For the question, are the n queries all given at the same time to the algorithm, or they are adapted to each other?
So the thing is that it will work even if we have all of the queries offline in the beginning. And it will even work if they are uniformly at random.
So the only reason you had deletion here was to unroll the updates?
Exactly.
But if you can ask all those queries beforehand, can you ask them all in parallel, the same data structure?
You have to use a huge graph, and because of that, you won't get as good.
You run the data structure, like you insert things, you run it for, like, you've inserted all the points into it.
Yes.
It's a data structure, so it has a, like, you just write down what the data structure is.
Yes.
Then
okay.
Separately start giving these queries to that data structure and write down the answer.
I don't think it will hold because the lower bound, so the error probability of the algorithm is for answering all of the updates simultaneously. And yeah, I think there will be a problem there, but yeah, we can think about it. Yes.
Sorry, one more question about this construction. Going back to the previous thing I asked, this isn't necessarily a bipartite graph, right? Because you have this like vertical edge there by default, right?
Well, it is just a union of some passes, some potential passes. So again, it is bipartite.
Okay. Yeah.
We can just
Right. Okay, cool.
yeah, so let's just make sure that we've understood how it works through this example. Let's think that this is our instance of inner product queries, these three. So we have three copies of the gadgets, and each one of these rows is the state of the graph at a certain time step. So in the beginning, we just add the vertical edges of the gadgets. Then we add the E1 edges for everyone that's the private bit is 1, which is the first one and the last one. We add those red edges. Then we move to the queries. For the first query, we have all ones. So we have to insert all of the green edges over there. The size of the maximum matching will be 2 here, which is 1 and 1. 1 for the middle one, which is 0 and 1, and again 2 for the last one because it's 1 and 1. So we have 5 overall, we subtract D, and we're left with 2, which is the answer of the inner product queries. Then we undo, so we remove all of the green edges. Note that we're back to how it was before this query. Then for the next one, we do the same thing. We add the green edges for the first two here because it's 1, 1, 0. And then again, here we have 2 on the first one, 1 on the second one, and 1 on the last one. It's 4 overall, and we subtract 3 because it's a dimension, and we have 1, which is the answer. Is it clear how it works? Yeah, okay. So as you can see, this reduction here, it's depended heavily on being able to remove edges so that we can undo whatever we've done for the query. So if we want to do it for insertions only and that's get that lower bound over there, we need a new gadget so that we can reset without removing. So in other words, we want to reset with even more insertions. The key observation here is that the size of maximum matching for a path of length 2j minus 1 or 2j is j. But for a path of length 2j plus 1, it's j plus 1. And this is going to be the two different cases of the AND gate that we want. So if we have this gadget like this over there, we have a path of length 2j minus 1 in the middle, and we have one edge E1 in the beginning and edge E2 in the end. And we do the exact same thing. We add E1 only if the private bit is 1, and we add E2 only if the query bit is 1. Again, the size of the maximum matching minus j here will be exactly the answer of the inner product. The nice thing about this gadget is that imagine that we have this gadget for j and we want to get to the gadget for j plus 1. We can only insert this edge E2 if it wasn't already inserted. Insert one more edge right here, and then put one potential edge for the E2 of the next gadget. And you're good for the next query as well. And again, note that this edge E1 is inserted once in the beginning. So the neighboring instances will again map to neighboring instances. So let's explain it more in the example on the way. So let's think of the same example. We have a private vector x equal to 1, 0, 1. So we have one potential path for each one of the entries. We insert the first edge only for the ones that the private bit is 1, which is the first and the last one. then we add the second edge for everyone, regardless of the query or the private bit. And the one after that, we only add it for the query. If the query bit is 1, which here is, again, all of them. So we have maximum matching of size 2 for the first one and the last one, which are the both 1 cases. And for the second one, we have a path of length 2 and hence maximum matching of size 1. And note that here we have to subtract j for each one of the entries because it was between j and j plus 1. So we subtract j times d, we're left with 2 again, which is the answer for this query. For the next query, we have to insert the next edge for everyone, regardless of the query, and the one after that, we only add it for the query bits that are 1, which is the first 2 here. Again, we have 2 passes of length 4, which have the maximum matching size of 2. And for the first one, we have a maximum matching of size 3 because it's 1 on 1. And then again here, we subtract this time 2 for each one of them. 2 times 3, 6 is subtracted from 7. And we're left with 1, which is the answer. Here, we have to do the resets with more insertions. So what is left over there, that 1 edge in the bottom row, we add that, everything's resetted, and at this point, it doesn't matter what the previous queries has been. So we move on to the next query, we add the next edge for everyone, and for the last query, we only have an insertion to be done for the last one. So we have a path of length 7 for the last one, and 5 and 6 over there, but they both map to maximum matching size 3. So we have 2 3s and 1 4, because we have 2 dot products of 0 and 1 1. So then we have a 10, and we have to subtract 3 times 3 here, and we're left with 1, which is the answer of the inner product. So to wrap it up, we did the reset with even more insertions. And note that here, because we have for omega d number of queries, we have d squared updates and d squared vertices. Here we have the lower bound of t to a minimum of t to 1/4 and n to 1/4 instead of square root n. So this.
Why could you not have taken the previous construction? I think this was the first thing, create b copies of that, and then when you have the next query, instead of resetting it, you just keep the first thing, don't change it, just add it to a new copy, and then like the answer will be that many maximum matches minus 2 minus 45 the previous count.
Sorry, I did not understand what.
So you had like a previous construction where you said you have to delete edges to make the moves, right?
Yes.
Why not just, if you have 2 queries, instead of deleting it, why not just create 2 copies of the initial thing? For the first query, you use the first copy.
Okay. So the problem with that is that we need to have 1 private edge for each one of those copies, and 2 neighboring instances of the inner product is now mapped to instances of the maximum matching that have this distance number of queries. So yeah, it will blow up. Yeah, so this concludes the first set of results that I wanted to talk about. So it's a good time to pause and see if there's anything unclear here. All good?
There's a small question usually in additive graphs. You hope for, or like in dream scenarios, even to get something much weaker, like 1 to 2 approximation or 1 plus epsilon approximation, which is translated to an additive error of epsilon n. You are operating at a much lower additive error.
Yeah.
Like does your result rule out, for instance, if I want 1 plus epsilon approximation?
So the thing is that for 1 plus epsilon is the private parameter, so let's get alpha. If we want a 1 plus alpha approximation with polylogarithmic additive errors, we have some results in insertions only. Like there are some results in the insertions only, but for fully dynamic, we don't even have that. So now we have this vague idea of resetting with even more insertions. Let's see what we can do with it for a completely different flavor of problems, which is norm estimation. Before getting to the setting of that problem, let's have this important definition here, top K norms. For any K from 1 to n, if we have a vector V, which is n-dimensional, to calculate this top K norm, we have to just sort it based on their absolute values and simply take the top K, one of them, and add them up. And so, for example, top 1 norm of any vector is the maximum absolute value, and the top n norm is exactly L1 because it's the sum of all of the absolute values. So the problem that we want to consider here is that we have a universe of n elements. At each one of the time steps, we have one insertion for each one of the updates, and we care about the frequency vector of these elements. So, which Fi is the number of insertions that we've had so far for the ice element. And our goal is to have an algorithm that calculates all of the top K norms at each one of the updates. And also it's differentially private, where we take the neighboring definition to be that two sequences are neighboring if they're different in only one of the insertions at one of the time steps. So it's event level. So before moving to the lower bound itself, let's see what we can do if we have a black box that solves all of the top K norms for us. So let's take, for example, this toy example. For some integer K star between 1 and n, which we don't know, we have that the value of the vector for F1 to Fk star is all J. And for which we know the number J. And for all of the other ones, the frequency, the value of that entry is J minus. And we want to understand what K star has been based on only the answers of the top K norms. So let's see what the top Ks of this example here are. Well, for K smaller than K star, it's simply just K times J because it's moving on, it's going up J by J. But after the point K star, it moves up by J minus 1. So if we plot it, the curve will look like this until the point K star, the slope of the top K norms will be J. And after that turning point, we have the slope J minus 1. And we're looking for finding that turning point where the slope changes from J to J minus 1. And if the algorithm is alpha accurate for all of the top K norms, the answer of the algorithm, the output of the algorithm will be in this, is it red? Let's say it's red, zone over here. So how can we find a good estimation of K star? Let's take a number K in our hand and set it to 1 in the beginning. We increase it 1 by 1 and assume that k is smaller than k star until we're proven wrong. How can we be proven wrong? Well, under the assumption that k is smaller than k star forever, we expect the output of the algorithm to be that purple area over there. So since this output is not working like that, and its slope goes down by 1 at some point, we expect it to exit this region at some point. And how can we be sure that this k out, which is the first k that proves us wrong, is a good estimation? Well, the width of this region over here and that purple region over there is both order of alpha. And the difference of these two slope top k queries, we expect this curve over there to be outside of this region. So using this black box that solves top k norms, we can find a good estimation of that turning point k star. Shout out to Uzir Sharon. So now let's go back to our reduction. So we want to reduce from inner product queries to this top k norms estimation problem. And we want to use this slope idea that we just talked about. So let's assume that we have d elements, so d is equal to n. And we have one elements corresponding to each one of the entries. Assume that somehow we've made it possible that at the time that we want to answer the J's query, the frequency of the ice element for every I is the value of its private bit xi plus j minus 1 plus the private bit qij. So now what does the histogram look like? For every entry that we have both ones, we have the frequency equal to j plus 1. For every one that we have 1 and 0, or 0 and 1, we have frequency exactly j. And for all of the both 0 cases, we have frequency j minus 1. And also note that in all of the arguments that we had in the previous slides, it will still work if the slope after that point k star is at most j minus 1. So now we have a frequency vector that looks like what I just said, and we are looking for the first turning point that the slope changes from j plus 1 to j. So now we can use that idea over there to get an order of alpha estimation of the answer of the inner product. So now let's see how we can make it work so that the frequencies are like this for the J query. Well, we first initialize all of the frequencies for all of the elements to the value of the private bit. So if the private bit is 1, we insert 1 to that element. And if it's 0, we just do a no-op. And it's important that we do a no-op instead of just skipping that, because we want them to map to neighboring instances. And for the J query, let's assume that the frequency is already xi plus j minus 1 from the previous query. For this one, we can just do the same thing. We can just insert 1 to everyone that qij is equal to 1 and do a no-op for others. Then do the slope thing and answer the query. And then we can just do the exact opposite of what we did in the beginning. So insert one if we didn't insert then, and do a no-op if we'd already done an insert. And actually doing a no-op in the query phase is not important though, because it's not private, the query vectors. And using this, we can get a lower bound of minimum of t to 1 fourth and square root n, because the dimension is the number of elements is d, and for answering d number of queries, we have order of d squared updates overall. And note that the querying is not taking us any time. We're expecting that the query is given to us at every time. So now you might be thinking, yeah, of course, this problem is hard. What did you expect from it? You're expecting the algorithm to answer all of the top K norms at all of the updates, and you want it to be private. Well, the thing is that if we allow a small multiplicative error, 1 plus alpha, and we allow a polylogarithmic in NNT additive error, we have an upper bound for that case that not only that solves all of these top K norms, it outputs a frequency vector synthetic to the previous, to the original frequency vector, that it can also estimate an even larger family of norms, which is monotone symmetric norms. This family contains not only all of the top K norms, but also all of the LP norms. So let's just have a quick overview of the other contributions of this paper. In this paper, we also gave the first lower bound for also the multiplicative error of a problem called one-way marginals. This problem to item level problems is what inner product queries is to event level problems. So it is, so to say, the go-to problem to reduce from for item level DP, continual DP. And so the problem is, yeah, we have time. The problem is that we have an n by d binary vector, a binary matrix, and we want to output a vector that is an estimation of the mean of each one of the columns. And note that the range of the output for each one of these entries is 1. So having a constant lower bound for it is a big deal. The previously known lower bound was, and also the, I forgot to mention that, 2 instances of this problem are neighboring if one entire row is different. So the previously known lower bound for this problem was that the additive error alpha has to be omega 1. We showed that the same omega 1 lower bound holds even for eta times alpha, where eta is the multiplicative error. And then using that as applications of that lower bound, we showed some item level continual DP lower bounds for a variety of graph problems. Note that since over there, omega 1 was the range of the answer anyway, this can give us polynomial lower bounds on the graph problems. And regarding what can be done in the future, well, first of all, as mentioned, we don't know much about the multiplicative error for fully dynamic problems. So it's an interesting problem to look at because we already have the upper bounds for insertions only. We have the lower bounds for no multiplicative error for fully dynamic. So that could be interesting to look at. And also, as again mentioned, the upper bounds for all of these t to 1/4 lower bounds that I mentioned is t to 1/3. And this seems to be quite the theme for these problems, and it's appearing a lot. So that could also be interesting to close down that gap. That's all I wanted to talk about today. Thank you for your attention.
What happens if you have a very sparse graph of maximum matching in terms of order? So your instances seem to be extremely sparse, so basically trees.
Yes. Yes.
Does the t to the 1/3 upper bound improves in that case?
I can't think of any results there.
But the upper bound works for arbitrary polynomial.
Yes.
Any other question? Not the sci-fi.